Your child practices the same math problem 10 times and still gets it wrong. They try to ride a bike and fall over repeatedly. They can't seem to remember the spelling of certain words. No matter how many times you drill them, you think, maybe they're just not good at this. You're wrong. What you're witnessing isn't failure. It's brain development in real time. Here's what most people don't understand about learning. Your brain doesn't grow when you succeed. It grows when you fail, specifically when you detect errors, adjust, and try again. This is called error-based learning. And it's the most powerful mechanism for skill acquisition that neuroscience has ever discovered. Let me show you what's happening inside your child's brain when they struggle. Deep in the frontal region sits a structure called the anterior cingulate cortex. This is your brain's error detection system. Every time you make a mistake, hit the wrong piano key, miscalculate an equation, misspell a word, this region fires off a signal called error-related negativity. It's like an alarm that says, hey, that didn't match the prediction. Adjust. This error signal is gold. It's the starting point for neural rewiring. When your brain detects a mismatch between what it expected and what actually happened, it immediately begins adjusting the neural pathways involved. It strengthens some connections, weakens others, and fine-tunes the entire network. This is neuroplasticity in action, and it only happens when there's an error to correct. Think about how a child learns to walk. They don't read a manual on biomechanics. They stand up, fall down, stand up, fall down. Each fall sends error signals to the cerebellum, the brain's movement coordinator. The cerebellum notes the balance failure and adjusts muscle timing for the next attempt. Fall after fall, the adjustments compound. Then one day, walking becomes automatic. Not because they stopped failing, because they failed enough times to build the neural circuit for balanced bipedal motion. This is the fundamental paradox of learning. You must fail to succeed. Not fail once and give up. Fail repeatedly while making micro-adjustments based on feedback. This is what separates kids who overcome challenges from kids who don't. It's not intelligence, it's error tolerance. But here's where it gets fascinating. The brain doesn't just detect errors, it predicts them. Before you even attempt an action, your brain constructs an internal model of what should happen. Neuroscientists call this predictive control. When you reach for a cup, your brain predicts the weight, the grip force needed, the trajectory. If the cup is heavier than predicted, you get an error signal. Next time, your brain adjusts the prediction. Kids who struggle with certain skills often have inaccurate internal models. A child who can't catch a ball isn't uncoordinated. Their brain's prediction of where the ball will be doesn't match reality. But with repeated attempts, repeated errors, the prediction becomes more accurate. The cerebellum recalibrates. The visual cortex refines its motion tracking. The motor cortex adjusts timing. Slowly, catching becomes natural. Now let's talk about repetition. Error detection starts the process, but repetition solidifies it. Every time you repeat an action, you strengthen the neural pathway involved. This strengthening has a physical basis, a substance called myelin. Myelin is the insulation around nerve fibers. The more you use a neural pathway, the thicker the myelin sheath becomes. Thicker myelin means faster, more accurate signal transmission. It's like upgrading from a dirt road to a highway. This is why musicians practice scales thousands of times. Why athletes drill fundamentals endlessly. They're literally building myelin-coated superhighways in their brains for those specific skills. But not all repetition is equal. Mindless repetition doesn't build skill. You need what psychologists call deliberate practice. This has three components. First, focused attention on the error. Second, immediate feedback. Third, incremental difficulty adjustment. Without these, you're just going through motions. With them, every repetition rewires your brain. Here's what this means for parents and teachers. When a child struggles, your response determines whether struggle becomes growth or shutdown. If you say, "You're just not good at math," you're telling their brain to stop trying. But if you say, "Your brain is building new pathways right now," the struggle means it's working. You're framing errors as progress. Research by Carol Dweck on growth mindset confirms this. Students who believe intelligence is fixed avoid challenges to protect their ego. Students who believe intelligence is malleable seek challenges to grow their abilities. And here's the kicker: the malleable belief is neurologically accurate. Your brain physically changes based on experience. So what do kids who overcome weaknesses have in common? First, metacognition. They notice their own errors. When they fail, they don't just feel bad. They analyze, I held the pencil too tight, I added before multiplying. I leaned too far forward. This self-monitoring activates the prefrontal cortex, which then guides behavioral adjustment. Second, they tolerate failure emotionally. They don't interpret errors as identity threats. They see them as information. This psychological safety is crucial because fear shuts down the prefrontal cortex. When you're anxious, your brain defaults to rigid habitual responses. You can't learn. Creating an environment where failure is safe literally enables neural plasticity. Third, they have executive function skills, working memory to hold the problem in mind, cognitive flexibility to try new approaches, and inhibitory control to resist, giving up when frustrated. These skills are trainable, but they require, you guessed it, error-based learning and repetition. Here's how to support error-based learning practically. First, ask questions instead of giving answers. What happened there? What could you change? How did that feel different from last time? These questions activate the error detection system and prefrontal analysis. Second, praise process over outcome. Not, you're so smart, but you tried 3 different strategies. Not perfect score, but you caught your own mistake and corrected it. This reinforces the behavior that actually drives learning. Third, make errors visible and analyzable. Video record a child attempting a physical skill, so they can see the gap between intention and execution. Keep an error log in math, showing what types of mistakes they make and how they fix them. The brain learns from patterns, and you can't see patterns without data. Fourth, structure practice for incremental challenge. Not so easy they succeed without effort. Not so hard they fail without learning. Right at the edge, where success requires full attention and small adjustments. This is the zone of proximal development, and it's where myelin builds fastest. Fifth, build routines that automate repeated skills. The goal isn't conscious competence forever. It's unconscious competence automaticity. When basic skills become automatic through repetition, working memory frees up for higher order thinking. Let me give you a concrete example. A child can't do pull-ups on the monkey bars. Don't drill pull-ups. That's too hard. Start with hanging, then pull their knees to chest while hanging. Then assisted pulls where you support some weight. Each level provides manageable error signals. The cerebellum and motor cortex make micro-adjustments. Myelin builds in the relevant pathways. Eventually, the full pull-up emerges. Same with reading. A child who can't decode multi-syllable words isn't bad at reading. Their phonemic awareness and orthographic mapping aren't fully developed. Break words into chunks. Let them make mistakes reading them. Provide immediate correction. Repeat with variations. The neural circuits for decoding strengthen with each error-adjusted attempt. The pattern is universal. Predict, attempt, detect error, adjust, repeat. This is how humans learn everything from walking to calculus. The only variable is how many cycles it takes, and that depends on starting skill level, quality of feedback, emotional safety, and sheer repetition volume. One final insight: watching someone else succeed doesn't teach your brain much, but watching someone else struggle, fail, adjust, and eventually succeed, that activates mirror neurons and provides a model for error-based learning. This is why peer learning and showing your own struggles as an adult are powerful teaching tools. If this video changed how you think about mistakes and learning, please hit that like button and subscribe for more neuroscience-based education content. Your support helps us reach more people with evidence that can transform how we teach and learn. Thank you for watching, and remember, your brain's favorite question isn't, am I smart enough? It's, what can I learn from this error? See you in the next video.